Hi everybody, in this video we are going to figure out how to describe lines in 3 dimensions. So let's get started. Let's start by talking about something we've done before, which is to think about the analog 1 dimension higher of some things that we know that live in 2 dimensions. So if we think about the circle that we know, and we know the equation for it, if we go up 1 dimension higher, we get the sphere. And looking at the equations for these two things, it looks like all we had to do was add a term that dealt with that z-axis, that dealt with that third dimension, and we went from the circle to the sphere. So we might think that we could do something similar to take lines into another dimension. If we think about the standard equation, standard form of the equation for some line, what if we just add a term that deals with z? What if we just break it into 3 dimensions? What is this thing going to be? Well, it doesn't end up being a line. It ends up being a plane. And if that seems strange, one way to maybe jog your intuition is imagine that if you fix z, if you pick some specific z to look at what's going on with some particular z value. So you fix z to some value. We're looking then at some fixed height. And what we see is that there are infinitely many pairs of x's and y's that would then work to solve the equation at that height for that given value of z. And we can do this for any different value of z we choose, and so since there are infinitely many points at every height, we can't be describing a line. And as we see here again, it ends up being the plane. So we're going to have to try something different to come up with how to describe lines in 3 dimensions. But to do that, I'd still like to start with ways we can think about how we describe lines in 2 dimensions in the plane. So if we look at the slope-intercept form of the equation for a line, what we can think about, one way we can think about this is that b, constant b, tells us enough information to know where the y-intercept for the line is. And then the slope really kind of tells me how to, from that point, get to any other point. All I have to do is keep the ratio of rise to run as I move left to right, up and down. I just have to keep that at that fixed ratio, and I'll always find other points on the line. So with some starting point, the slope then just sort of tells me what direction I can head in to end up at other points on the line. And hopefully thinking about the slope-intercept form in those terms makes us think about vectors. And indeed, we can use vectors to come up with a different way to describe lines in the plane. So if we've got some point on a line, say with coordinates x1, y1, we could just as well talk about a vector. As long as we fix the base point at the origin, there's some vector with components x1, y1 that leads us from the origin to that point P. And the only other thing we need then is a vector that points in the direction of our line, sort of as parallel to it, and whatever the components of that might be. With the vector that leads us from the origin to the point on our line and a vector in the direction of our line, then if I add those two vectors, I notice that leaving from the origin, that also gets me to another point on my line. And I don't just have to add the vector p plus the vector v. I could actually take the vector p and add to it any scalar multiple of v. And if we do that, we see that for different values of the scalar multiple, we get to different points, but I'm always ending up at some point on the line. And so we can write down the vector whose components get me from the origin to a point on the line. And it's just some scalar multiple of v. We call that scalar t the parameter. So we can get to the parametric equations from here because since this vector is fixed at the origin, its components are the coordinates of a point on the line. So we can write down the parametric equations for the line in terms of that parameter. But you pick any value for that parameter t and plug into these two equations, and you'll get the x and y coordinates of points on the line. So this is another way to describe a line in 2 dimensions using what we know about vectors. So take a moment and see if you can figure out what the parametric equations for a line passing through these 2 points would be. Okay, and we'll talk about this in class next time. But the good news is that figuring out how to describe lines in this way in 2 dimensions is actually doing most of the work to getting us to 3 dimensions, because this will scale up nicely 1 dimension higher. We still just need a vector p that gets me from the origin to some point on my line, and I need a vector v that points in the same direction as my line that's parallel to it. And with those 2 things in hand, I can once again take p and add to it scalar multiples of v, and different values for that scalar multiple, different values for that parameter get me to different points, but all those points end up on our line. So this diagram's a little bit busy, so take a moment and sort of make sure that this all makes sense, what we're doing here, and see that it works the exact same way, that I can again describe all the points on a line in terms of some parameter in three dimensions. This works very nicely. Okay, so if I've got some point in 3-dimensional space, x1, y1, z1, and I've got a vector that is parallel to that line, or points in the same direction, points along the direction of the line, then I can get, much like in 2 dimensions, the 3-dimensional parametric equations for that line. And the only other thing we want to talk about then is that if I take the parametric equations for a line, and so if I take the first equation, I can solve for x in terms of, solve for t in terms of some stuff involving x, and in the second equation I can solve for t in terms of some stuff involving y, and the third equation I can solve for t in terms of some stuff involving z. And since we're talking about the same parameter every time, I can set those things equal to each other, and so what we end up with is what you see here, and these are known as the symmetric equations for a line in 3 dimensions. So using what we know about vectors, we can come up with the parametric equations, and then with a little bit of algebra that I hope you will take the time to stop and make sure you're good with, we come up with the symmetric equations. So look through this stuff again, and I'll see you in class.